So let me put myself up and also let's see. So let me talk a little bit about today's talk. Basically, in this talk, we are going to see a different angle looking diversity exploitation, wideband channels. We are going to ask some fundamental questions about what is the most efficient way to exploit diversity. And so basically, what I want to show you outline of this talk. I will first start with the introduction, and we will talk a little bit about what interests to us, and then we are going to make observations based on current developments in the data communication, especially wireless communication framework, and we are going to ask some fundamental questions about what is the trade-offs between systems that are operating rich multipath, such as the proposed wideband systems or wireless metropolitan systems, versus the local area networks. And we are going to develop a framework for space frequency coding, which is very similar to space-time coding, but we are going to have a different way of looking at how we design the codes for this space frequency coding system. And then we are going to ask ourselves, well, is there an optimum way of exploiting diversity such that we don't lose too much rate? Because when you want to exploit diversity, that means you have to have some redundancy. And so there is a trade-off of how much redundancy do you need versus how high rate can you achieve. And then we are going to talk a little bit about our observations, and we are going to end with some conclusions. So let me talk about the issue for diversity. The diversity topic has been around for a long time. Diversity, when people first started talking about diversity, they were talking about diversity, for example, due to the change of the channel, time variation of the channel. In particular, I'm not going to be talking about that. I'm going to be talking about wideband channels. And those of you who are familiar with wideband channels, you know that you want to partition sometimes these channels very finely. So in most cases, the time variation is either negligible or it's manageable. And you don't have too much diversity on the time axis, but you have other diversities in the spatial axis or spectral axis. So that's what we are going to talk about. So the analysis of diversity here will be slightly different. Now I want to motivate this talk with thinking about these lands which are extremely popular, and also look into the evolving generation of personal area networks and short-range systems, which relate to very much to WINLAB topics like info stations and other things. And I also want to motivate this talk with the wireless wide area networks, which we have done a lot of work in terms of synchronization and receiver. Zongan has done a lot of work in those areas, especially for intermediate assignment schemes. So the question that I think one has to think about is, how do we best exploit diversity in any of these systems? Okay. So what is the least costly way of exploiting diversity if I want to use something like ultra-wideband? What is the least expensive way of doing it if I want to use a wide area metropolitan network? And if I want to do it with something like a LAN, how do I do it? Do I just slap on some schemes from space-time coding with something like COFDM or that kind of modulation, and do I think that that's the best way to go about it? So let's look into this, the paradigm shifts. Basically, we see that, why am I talking about data services? Because it looks like the data-oriented systems, like the Wi-Fi systems, they're eclipsing the 3G in terms of a medium for data transmission for wireless systems. And now we are saying, people are saying, well, 802.16, wireless metropolitan area. People are saying, oh, the same thing that happened to 3G will happen to Wi-Fi. I don't know if this is true. And people are saying the same thing for ultra-wide. They're saying, okay, wow, we're going to have ultra-wideband. It's so good. We can put like storage area networks based on these wide area, based on this technology. We can do all sorts of, we can replace our monitor cables, cut any buses from our computer chips. We can just interface everything together with ultra-wideband. Now we are going to talk about what's the advantage of these schemes. Okay. Now, the main advantage that I see for ultra-wideband right now is the following. You look at the first generation ultra-wideband. It has 128 carriers over 500 megahertz. Okay. So these black carriers that I put are the ones that are modulated right now. And the red ones that I just put in the background, these exist like every 3 carriers out of 4 right now. In the first generation, they will not be modulated. So you look at the rate of this kind of system, especially considering that people are trying to do VPSK type of modulation on these systems. The total throughput on these systems will be about the same throughput as the maximum throughput on the Wi-Fi 802.11a type of system. Okay, that's not going to be much higher. It's going to be 120 goods, in terms of throughput, and then you can have on Wi-Fi systems 108. Most vendors do actually ship with 108 megabits per second. So the throughput is not different. Okay, and most people are not really asking for increased throughput. They are really asking for increased reliability.
You're just saying like binary.
Yeah, in terms of bits. Even though you occupy a much smaller bandwidth, ultra-wideband systems are really catering to the issue of diversity right now. It will, maybe in time, they will be catering to the exploitation of this bandwidth in a very efficient manner. But the first generation will be, and this ultra-wideband I have is, I want to be clear on this. This is the banded OFDM type proposals that are going into 803.15, which are, basically backed by everybody other than Motorola and Extreme Spectrum.
Do you know anything about that? Are they planning to sell like binary on each carrier? Or
The first generation is binary.
On every carrier?
On every carrier, because the transmission spectrum is much lower than what you can transfer.
So they're going to do a multi-carrier over 500 megahertz?
That's the
and it's 128 carriers?
Right.
And is 128 the number they're using, or is
they're using? That's what they're.
What is it that you said? Oh, the red ones they're not being used.
That's right. This is a fully interleaved setup where you have you do not use 3 out of there's, if you look at the spacing, this is like the first carrier, this is the 5th carrier, 9th, etc. So they do not use a large percentage of this. This is the low rate systems that will be the first ones to come out.
Okay, I just want to make sure I understand. So in fact, if you counted the red carriers, there's like 3 times or 4 times 128.
No. Out of 128, only the 32 will be used.
And each one of them sends binary.
Right now, yeah.
Independently?
Right now. Yeah, each one sends binary independently. So this is the first generation. Maybe in the future they will put 64, 1024 QAM on these, but right now the first generation will be binary.
And each one of these is about 5 megahertz or something.
Spacing, each megahertz, right? But you actually look at the actual one, the spacing is 4 times that, because you don't use 3 of those. Okay? This is called low rate mode of the ultra wideband. This is the first product that will come out.
You're saying 32 will not be used?
Will be used.
And the rest will not?
Yes.
So it means the effective bandwidth is 5 times 32, 150 megahertz?
No, because what's going to happen is that if you look at the bandwidth, these are not just some deltas, they are like some stink shaped, so that you are actually occupying the whole bandwidth. We can come back to it.
So each carrier is somehow doing symbol rates corresponding to 20 megahertz or 5 megahertz of the 32 carriers you use, right? Is each one on each carrier? Are you signaling at like 5 megahertz?
You are signaling about 5, and you have 32 of those. So your peak is, I believe, on the order of 150, 160. No, your peak is 128. If you count it, it's 4 megahertz.
Yeah, okay.
It's 4 megahertz, not 5, but 4 megahertz. And you are doing some basic VPSK type.
And you are throwing all the other
80
degrees of freedom for pulse shaping or for spectrum shaping?
Not necessarily. This is really for efficient FFT implementation. It's basically for to meet the challenge of FCC. For the first generation, you have to occupy 500 megahertz. They are going to occupy 500 megahertz. So that's the main reason.
By really having about 160 megahertz occupied.
No, because these are things.
Well, they're going to be all these little zeros.
They won't be. They may go to zeros, but they're yeah. You put them up. Yeah. It will not be. It will be passing to zeros at exactly the right frequencies, but anywhere else they will not be zeros.
Okay.
So that's the. And I'll tell you some other things that
But it brings up a good question when FCC defines a 500 megahertz bandwidth. What does it mean by that? Is it 3 dB bandwidth? Is it
Well, this is a good question. I don't know the answer to that, but I just tell you what I what my reading on this is. This is exactly the same type of assignment as in the OFDMA mode for the 802.16. In the OFDMA for the OFDMA mode for the 802.16, you still have 20 megahertz, but you actually operate at a much longer multipath. So it is analogous to ultra wideband. It scales. The scale, if you scale the multipath support to the symboling rate, it will be exactly like this. In that case, you have 2,000 carriers, okay? And carriers are separated by how many? 64 or 32? How many carriers? They are separated by
64 each sub-channel. 32 sub-channels.
There are 32 sub-channels.
32, yes.
32 sub-channels, exactly analogous to this. So, and they are separated by 64 carriers. So this type of system maximizes diversity. Okay. So when I say diversity, I mean it maximizes frequency diversity. That's why, you know, I'm talking about the apples-to-apples comparison between something that's wideband, where you actually have an interleaf setup. The same thing that I'm talking about in ultra-wideband, you can scale that to the metropolitan systems for the OFDMA modes, and it's exactly the same idea. So the gist of, you know, since we started this, the gist of what I want to discuss now is, in these systems, clearly there's diversity in the frequency domain. Actually, this plot that I have is an extremely pessimistic one. But what I wanted to highlight was, if you look at a channel, for example, you could have like how many channels here? You could have 20, 25 channels in what ultra-wideband occupies. And you can find that in one of those channels, you won't have too many channel difference. Well, you may say, okay, well, what kind of channel is this? Well, it's a channel maybe with a multipath, which is, you know, delayed from the main signal, maybe less than a sample, maybe 1/10 of a sample apart. That's still considered wideband, quote-unquote wideband, that requires equalization. Okay. If you want to equalize, so you cannot do these things without equalization. So people who do OFDM, they said, oh, well, instead of equalization, I'm going to do coding, and I'm going to use this coding for my benefit. The question is, how much diversity is there in these typical LAN environments? And to give you an idea, we are going to talk a little bit about, we'll give some parameters about those. Typically, the root mean square spread of the LAN environment is one sample space, 50 nanoseconds. In a signaling, you're signaling 20 mega symbols per second. That's like one sample. Okay, maybe a little more than what I show here, but not much more.
You say one sample, you mean one symbol?
That's a good question. You can call it a symbol. I don't want to call it a symbol because a lot of people, especially in OFDM, they call a symbol the block symbol.
Yeah, I understand.
Yeah,
but
you can call it a symbol.
If you take that one single carrier, it's like one symbol.
That's right, that's right. If that's the way you understand it, then we can.
I'm just curious.
Right. So let's talk our observation from Wi-Fi. I have some friends from Intel and other places. They told me that nobody really cares too much about increasing the range of their Wi-Fi network. Most people are really talking about reliability. That is, how does this thing perform when it's out of, you know, a certain range? You still want it to maintain a connection. You still want it to operate in the high QAM modes. Like you look at Wi-Fi system, for example. You want to operate it in the as it can operate, and you don't want to drop your connection for whatever reason. And what is the measure for this? There are many measures. You know, there's also capacity measure, and there are other measures. In this case, I'm going to say, okay, my measure will be error rate. So my question will be, well, if I want to exploit this diversity, how can I design codes that take optimum advantage of this diversity to minimize my bit error rate? So that's my goal, and that's my comparison. Now, if you look at this system, given that, you know, FCC gives you a total transmit power which is limited to a certain power in this, you know, Wi-Fi systems, people have said, okay, can we slap, for example, space-time coding on top of these OFDM-like systems? And in 2002, for example, people from AT&T Labs, my friend Stamoulis, Nafal, and they went to several conferences, CISS here, ICC, etc. Basically, they talked about, you know, how you can actually implement space-time coding on top of these block modulation schemes. They are not the only ones who did that, but you can actually find more coverage of this in this book, a recent book by Nokia people, Heskel and Tureli. They have very good coverage about, you know, the space-time coding applications to frequency selective channels, or if you may say for OFDM-based modulation schemes. Now, why OFDM? Because all those things, 802.15, 803.15, 802.16, 802.11a G modes, really, these are really OFDM-based schemes. So I want to just level the playing field. So I want to motivate it by saying, okay, we want to have, for example, some kind of OFDM type scheme for frequency diversity exploitation. do we want to just slap some space-time coding on top of it? And people have done this study, and they came up with interesting results. And what we are going to talk about is very similar to space-time coding. Actually, you know, a recent paper by Su and KJ Liu in the November issue of the special issue on MIMO system in the Chinese signal processing, they actually show that, you know, you can express any space frequency code that we are going to describe in terms of a space-time code. Of course, I mean, especially any for block or in terms of trellis type code, you can do that. But the question is, are these things, if you just slap this space-time concept which was developed for narrowband systems with something that wants to exploit diversity, you know, how good is your performance? Okay.
So are you going to talk about what slapping means exactly?
What is?
When you say slap.
Slap means basically you say, okay, space-time is hot, OFDM is hot, I'm going to have space-time block coded OFDM.
Yeah,
okay?
but like, is there different ways of slapping?
That's right. That's what we are going to. I'm going to show. Yeah. And let's talk a little bit about this. So in the LAN environment, the major challenge is the diversity is not really there. Okay. Well, you have to equalize because there is some multipath, but the equalization kills your diversity. On top of that, you don't have the time variation that you have in other communication systems. So your code requires some kind of diversity. If you have some kind of code, area control code. So you need this diversity somehow. So what do? We create diversity. So we are going to look into systems which have some transmitted diversity or receiver diversity. In particular, I'm going to look at systems that have some transmitted diversity. Plus, I'm going to limit myself in this talk to block type schemes. Okay, I'm not going to be looking at trellis type methods of doing it, although that could be an interesting topic by itself. And I'm going to make this observation. I'm going to say, how does this spatial diversity that I'm going to introduce, how does that map to spectral diversity? Because it's of interest, especially when I want to compare, you know, the performance that I'm going to get with adding diversity in terms of spatial diversity to these systems. I want to compare how that compares to those systems that already have diversity, number one. Okay. So then I can make some qualitative measurements. Number two, I want to know if MIMO ultra-wideband is a good thing. I want to know if MIMO WiMAX, which is this wireless metropolitan access, is a good thing. I want to know if really there's a reason for doing that. And so first I motivate myself saying, okay, in the LAN environment I have a spread of 15 nanoseconds, up to one sample or one symbol delay, if you want to call it. Okay? Now, space-time coding was designed by, you know, you look at the earliest papers, and also the ones which I'm going to regard as, you know, for block type systems, Alamudi, for example. Right? Very simple, very nice, but it was designed for flat fading channels. Flat fading means not frequency selective fading. So a lot of people say, oh, what would happen if you have multipath? Well, they actually show that if you have multipath, you know, you'll have some performance degradation. Like what? You'll have some bit error rate, increase. And actually, if you look at this book that I gave, they actually have nice, MATLAB figures and curves that you can do on your own. And you will find that some people said, okay, well, I have to do equalization. Okay? So these people who said, I want to do equalization, they said, well, if you don't do equalization, then you'll have bit error rates. Okay? So I have to do equalization. But when you do equalization, what are you doing? You're killing the diversity due to multipath. So that's not the optimal way to do that. So these are some of the recent people who did that. Mitra from UCLA, Aktash at the University of Melbourne, Australia. So they have some recent papers, I believe, in the special issue again on the MIMO systems. And so we want to look at a different perspective. Okay? We want to ask ourselves, can I design codes thinking of exploiting this spectral diversity that optimizes the metric? What is the metric? Bit error rate. When I say optimize, of course, it means minimizes the bit error rate. So, where did this idea start? Well, the idea started from Goskay and Polaj at Stanford University in about the year 2000. There are some publications in 2000, 2001. But there are some problems with their approach, and not many people have followed up with what they did. And I'll tell you a couple of things that are the problems. Number one, they do fully understand what the problem is, and they do state, okay, what is the what
they don't fully understand.
They fully understand the problem, but they do not have the perfect code. Okay? So we are going to actually compare our performance to their code. So what they did was they said, okay, we fully understand this problem. We look at the bounds for this problem, and they developed the bounds for this problem. But they do not have a criteria for exploiting this diversity in the most efficient way, in the most optimum way. Okay? So that's really what I want to talk a little bit about. Okay. So I want to talk a little bit about this MIMO implementation of space-time codes, and I want to talk in terms of what kind of codes I'm going to develop. Well, I want to develop some set of codes that consists of maybe a set of M symbols. Okay, these are vector codes. They are applied on frequency domain. This index n is the number of frequencies that you have in your system. Okay, so what you see here is perhaps that m may be equal or less than n. Okay, and the difference that we are going to actually exploit is maybe if you want to operate in frequency selective channels and you want to exploit this whole diversity, that m has to be less than n. Okay. We are going to assume that we are going to have T transmit antennas. We are going to assume that we have R receive antennas. Okay. And basically, if I do some Fourier transforms, I'm assuming perfect synchronization in terms of carrier synchronization, other things. So if I assume that I do a fast Fourier transform at each of my antennas, okay, I'm going to find that whatever the signal amplitude was scaled by the channel times whatever the code was, I should be able to receive on my antennas. Now, how should I do my code design? My code design should be done in a way that minimizes the probability of error. What's the probability of error? It's the probability that you transmit the code C and then you ended up with code E. Right? And what is the bound for this? One of the bounds for this is the channel bound. It's the upper bound for the pairwise error probability. So one could say, okay, if this is my bound, okay, and this is the distance that I am going to operate at, what is this distance really? You know, algebraically, what is this distance? I think that the major difference that we have from most guys is we actually developed the algebraic model for this distance. Now, we are going to make some assumptions, and I will talk about the assumptions later, but one of the assumptions that we are going to make is, we are going to make an assumption that the channel we have is finite impulse response, it has a finite support, and on top of that, we are going to make another assumption. We are going to assume that we have some uniform distribution in this interval. So this is
uniform distribution on
the support. On the support, so the multipath could be coming anywhere on this uniform distribution.
Oh, you mean in the delays?
Yeah, the delays you have, so they are not like the probability of those are not exponentially weighted or some other form. So this is the same assumption both guys did, but the difference is that we are going to say, okay, what's the algebraic formulation for this? So we are going to develop a formulation in terms of a parallel subspace. So basically, what is the idea here? The idea is that if I want to think about the subspace that's spanned by each of these codes, by the way, that has to be like a fancy clover here. If I look at this subspace that's spanned by this code itself, the delayed versions of the code up to the support of the channel. Let's assume that the support of the channel is L. Okay. Now in this case, I'm going to assume this L is limited to 1 or 2. For LAN systems, as I told you, you can assume L equals 1. RMS spread is about 1, and you know, you can actually have systems that have higher support, and you can put L equals 2, etc. But in general, this L could be any arbitrary number. But you know, in practice, you know, in the LAN environment, they are going to correspond to 2. So
what is the range of your communication? How many meters you assume?
That's a very good question. In this case, you are assuming a limited room type environment. You are assuming your RMS spread is on the order of a 1 sample. So I want you to, if you want to calculate this, you're going to find that this would correspond to about the maximum difference between users about 15 meters, right? 50 nanoseconds times 3 times 8, about 15 meters. So this would be the range maybe in a small room. You think about the delays between different users. So, so this A is a diagonal matrix, and if you think about what this diagonal matrix is, it's basically corresponds to the fact that, you know, when you get a delayed version of a code, if you want to think of it in frequency domain, it's basically a modulation. It's a delay in time domain. It's basically a modulation in the frequency domain. So that's what this diagonal matrix is about. Now, there are several ways that you can design the codes. One of them is you can say, well, I'm going to make sure that this difference matrix between the codes, okay, is this parallel subspace is full rank. Okay? And if you want to pursue that, you're going to find out what is the maximum rank that this can have. You're going to find it's going to be the transmitters, number of transmitter times the support of the channel. Okay? So that's one criteria. Now there is another criteria, and that's really for high signal-to-noise ratio. It's basically the minimum eigenvalue, okay, of this difference of the parallel subspace. Okay? So this would dominate your response at high signal-to-noise ratio. So just for reference, I'm going to say, okay, well, if I want to, somehow estimate this code at my receiver, what will I do? Let's assume that we have full channel knowledge. This can be generalized to differential case, but I'm just going to assume if I want to estimate this what was transmitted, this is what I do, right? If I know the channel, basically I try to minimize over this code space, and I try to find what code was transmitted. Right?
What's the norm?
Which one? This one? This one is A here.
It's a what?
A.
He asked me what's the norm. What kind of norm?
What kind of norm?
This one?
Yeah.
This is a okay. This is a okay. This is a 2 norm, but it has the index that you have here is an A. A. Okay, so
it's a skewed 2 norm.
Right. It's a weighted.
Weighted, yeah. And 1 over TL is.
It's basically this is the number of transmitters you have. This is the support of your channel. Now, what you're going to find is that the number of carriers in your system is much larger than the number of transmitters times the number of the support of your channel.
Say that again. You're going to find. You could say it again. Whatever you just said.
Okay. The number of frequency carriers you have is much larger than the product of this number of transmitters times the number of the support of your channel. Okay. So what that means is that maybe it's not the best idea. To try to use all the subcarriers at the same time, because the only requirement you have is that this thing is full rank. You can still have it full rank if you do not spread to all the subcarriers. So it's not necessary that if you can actually have some kind of grouping when you design these codes. That, for example, you have a data that you want to transmit, a bit that you want to transmit. You don't necessarily have to put it on all the subcarriers. You can actually group it in a lesser set of subcarriers.
Group in what sense? You mean send one bit onto multiple carriers?
Well, you can think of it like a blocking. Okay. So one way that you can do it is you say, okay, well, I have a encoder pool. Okay. So I have some block of data that I want to send. You can separately encode different portions of these blocks. You can think of this as the easiest way to do that would be if you actually separated them in frequency domain. Because you have some bits that you want to transmit, like you have 2 bits to transmit, right? You can actually encode them, let's say, on 4 carriers. You don't have to encode like 2 bits that you have on all the subcarriers. You do not need to. So what is this really coming to? Well, it's coming to this whole argument about wideband versus narrowband again. So if you want to have a system that maximizes the frequency diversity, and you actually have limited multipath support, maybe you do not need to transmit at all the subcarriers. So this is, so you can actually use a subset of your available bandwidth for your coding. So this is one framework that we are trying to develop, that we are saying, okay, if we have, for example, T equals 2, L equals 2, for example, 2 transmitters, and the multipath support is 2, I will actually separate this whole n subcarriers into so many different blocks. So I do not have, the complexity of my decoding operation can be reduced, number 1. Number 2, I'm trying to tie this up with, how much frequency resource do I need if I do not have that much diversity to begin with. Okay. So if I want to do some group coding, okay. So what I do is I say, okay, I'm going to develop some kind of cyclic group code, and I'm going to actually, this is going to be fairly interesting development here. Why? Because I'm going to make some observations. I'm going to say, well, if I say that my codes are designed orthogonal at the transmitter, so that they can best, optimize the exploitation of diversity on these channels. If I say, okay, well, I have some cyclic codes that they're generated from an initial starting vector, but they actually end up with codes that are, if you want to think about it, like if you have one antenna transmitting a certain code, we actually show that the optimum code to use in this framework for another antenna is a cyclic shifted version of that code. Just like what YINLAB did in 1998 framework, they said, well, if you don't have too much diversity in OFDM systems, just delay that signal, make it like a virtual multipath. Okay? And some people like Hübner in Germany, like this summer, they actually show that that's the way you maximize diversity. But none of these people show that this would be the best way to exploit that diversity. Yeah.
Last question. I just try to understand the analysis in previous slides.
Sure.
People that actually this criterion, the analysis before this slide, it seems it's just similar to space-time coding. Is that right?
Exactly. This criteria
yeah,
is from Harold's paper.
Yeah.
Right?
Okay. I just want to ask. So here we have a subcarrier in frequency domain, right?
That's right.
Do you assume independence channel across across?
No.
So this is the difference between the space frequency coding versus space-time coding. Space-time coding, usually we assume independent channel from one time sample to another, right?
No, you actually assume the same channel from one time instant to the other. You just assume different channels between one transmitter to the next transmitter.
No, but the independence, the channels,
you just assume
the
independence.
random variable are independent.
You only assume independence between the channels. You're not assuming it. When you do space-time coding, you do not really say, well, my channel is changing from my sample instance to sample. If you look at, for example, Alumni, it's clear that the channel is assumed fixed. So you're not really exploiting time diversity in space-time coding. You are exploiting the spatial diversity.
So you mean in space-time coding, you only explore the space diversity.
That's right.
You don't have the time diversity. Actually,
Most generally.
So your H matrices is fixed throughout the whole time.
Well, they could change. I mean, you could relax some of those constraints. But actually, I look at literature. Some people assume they are fixed for thousands of blocks.
Okay. So
Even though it is the kind of feature.
Okay. So now the difference in space frequency coding is that the channel changes from one frequency domain to another. So I just try to understand the difference.
That's excellent that you pointed that out. But let me point out the interesting thing here. The channel support is limited. What that means is that the channels are highly correlated between different frequencies. But the question is here: if I'm trying to transmit something in frequency domain, and I'm trying to have this criteria that I want to find this code. Maybe this is using an ML decoder. What am I trying to do? I'm trying to maximize this distance. Okay.
Yes.
So I'm trying to figure out, okay, what is the minimum eigenvalue of this, difference matrix. Okay. So then I try to figure out, how should I design codes for the system. So the issue is when you have multipath, when you have these effect of a channel on these codes that you transmit, this channel, even if you design the codes to be orthogonal, they will not be orthogonal. Okay? You are going to have some kind of error. So you're trying to maximize when you design code. You're trying to maximize the separation between these codes. And you are asking yourself, how do I construct these codes? Not just like a random construction, but you're asking yourself, okay, how do I have a schematic construction of the codes? So I optimally exploit this diversity. So that's really what we're trying to do. And what it boils down to, that's the interesting thing, is that we are going to come up with how do you find the initial codes, but after that, for the multiple antennas, the optimum exploitation is if you have just circularly delayed copies of the same code at multiple antennas. That's good enough, and that's what YINLAB did. But he didn't really. Many of those people who exploit diversity, they just assume whatever code you use. They don't really think about this in terms of space-time coding. They just think of it like, okay, I have an extra multipath. It's like it's going to give me some diversity in my channel. It's like a fake multipath that will help my frequency diversity. Okay. So I'm going to state some of these theorems, and the details can be found in a paper that we are going to submit to transactions on Chrome at the end of December. and we already have posted our submissions to WCNC and ICC. So basically, we can think of this statement in terms of the following theorems. We are going to say that, well, if we have this code generated calligraphic G, if it has this structure, okay, that it is this G, the generating matrices, if they are diagonal, okay, then this parallel distance between the different generator, the codes that are generated from these two initial vectors will be maximized, okay, and these codes, if will be optimized, okay, if these initial vectors are somehow normalized in terms of the way that they are in terms of the way that their norm is set up, and basically we are going to say that we are going to find all these groups that we find, okay, will basically end up that when we talk about the groups, what we mean is when we look at the transmitter streams for different antennas, we are going to find that they are exactly cyclic shifted copies of the code that you transmit from one antenna. Okay. So what is the interesting thing here? The interesting thing I think here is, if you want to exploit the frequency diversity optimally, it is as if you are adding a multipath to your system. Okay. So people are saying, okay, let's have MIMO on top of a limited support system like wireless LAN. Right? But what you are doing with MIMO is effectively you are adding these multipaths, you are adding frequency selectivity. Okay. So the question is, if I already have that to begin with in a wide area network or in an ultra wideband system, do I need this kind of diversity? Because this space-time diversity that I have, or space frequency diversity, it actually transforms itself to a spectral diversity. So let me give you some performance figures for this. Basically, the idea of the cyclic shifts having full spatial diversity is not our idea. It's actually been shown by Hübner in Germany and this summer in several of their papers that it indeed does maximize the diversity if you have cyclic shifts from multiple transmitter antennas. And we have some performance figures for what we did and what other people did. Now I want you to look at this SNR plots. These start at -15. Okay, so when we talk about range, what we are saying is one of the reasons you want to use a MIMO system is sometimes you want to extend your range. Okay, you want to operate in very hostile environments. Now you find that these the code that we have, this lowest curve, we have this code that assumes that there are two transmitters. It also assumes that the multipath support is equal to 2. Now the way that we construct this code, same with both guys, that to maximize this distance between the codes, we will need to have a rate that is equal to 1 over the number of transmitters times the channel length. So the rate of this, both of these curves is 1 over 4. Now if you do some plain Alumuti style rate 1 type code, this is the best you can do, okay? So this is like 0 dB. So if you look at curves for most Alumuti codes, they actually start at this point. We're actually looking at very low SNR. And what we find is that if you increase the number of receive antennas in the Alumuti style, okay, you can do a little better. Now I also want to talk a little bit about the algorithm that was presented by Su in this special MIMO issue, Su and KJ. I think it's a very interesting paper because it basically shows that each space-time code can be considered a space frequency code and the space frequency code as a straight-time code. But the thing is, if you start with a space-time code and you transform it into a space frequency code, it's the same thing. Okay, the performance of that thing is not better than a plain Alumuti style. So if you start with an Alumuti and then say, okay, I'm going to transform that into some frequency domain signal, but in the process you say, well, I have to reduce my rate 1/2 because now I know the multipath support. You do a little better, but not really much better than a plain Alumuti. Okay. And you see that you can do a lot better if you can optimally code across a frequency selective channel. Yeah.
It's really hard to compare because some of these codes are rate 1 and other codes are rate 1/4, so there is inherent coding gain there.
That's right. That's right.
So
That's exactly right. So
it's like apple and orange in comparison.
this is correct. But one of the things that we want to keep in mind is, for example, rate 1/2. If I wanted to continue this curve, the student didn't do that. But it's very easy. I mean, just go to this book by Haskell and Terry. This curve, you go to 20 dB. This curve this aluminum is somewhere here. Okay. So there isn't much that you can do with even with this type of holding and repetitive type stuff. This curve and this two receiver case comes down here somewhere at 30 dB. Okay. So what I'm showing is considerably, markedly improvement. So it's not just a simple improvement. Now, the question you ask is actually, I think, a very good question in the sense that, if you wanted to have the same rate using some aluminum style, what could you have done? I guess you could have done repetitive coating, I mean the simplest way. You could have probably done some other kind of intelligent way of doing it. But this is really the competition. Aluminum is what is usually considered to be, a starting point for a block, space-time block code. And it does perform well, okay, if you have multiple receiver antennas and you have extremely high signal-to-noise ratio. It does perform okay. But if you want to operate in these regions where these codes cannot, why? Because you want to support these regions where the signal-to-noise ratio is not so high. So you're talking about a reliability issue. So you find that space frequency codes give you some advantage, like the way Boskai did, and in the framework that we give, the code construction we give, gives you a further advantage. Okay. So what's the trade-off? The trade-off is, so far, the decoder and decoder pair we have, we do not really, the way that we designed it, it's kind of complicated. Okay. But we are hoping that maybe it can be simplified because of the algebraic structure that we started with, because we started with the Krylov subspace method. Maybe it may lend itself nicely to some kind of iterative receiver. So there's a possibility that it can be handled in that fashion. So right now, what we are saying is that if there is little diversity, use MIMO. If there is little diversity in the system, you don't have too much multipath, use MIMO. And effectively what that MIMO will do, if you do it in an optimal fashion, is it will emulate multipath. It will emulate the channel, okay, for wideband. And, but if you have diversity existing in the system, we're going to find this kind of optimum code will actually, the rate of this code will go down as the multipath source goes up. So if you have ultra wideband, which has quite a bit of multipath samples, you use some code like this, your rate is going to go down considerably. And what are you going to gain? Not much. Okay? So the question is, extra diversity is not something good. If you can exploit the diversity in frequency domain, then just do it. So maybe, don't try to pair up MIMO with maybe something like 802.16. Don't try to pair up MIMO with something like ultra wideband. Because if you want to exploit both, you're going to find that you're not getting much. You're going to give up a lot to your, in terms of the coding. Okay. Now, what is the future work on this? Basically, this rate improvement, basically this rate is, as I said, it's limited by the number of transmitter antennas and the just channel support. So we are thinking of ways to increase the rate. And the second thing is we are thinking of how can we take this to a multi-user setup. Okay, so this idea is primarily a single-user application. Okay? And of course, you know that in most scenarios, especially in frequency selective channels, it's of great interest to have a multi-user exploitation of this diversity. And people have used scheduling and other types of methods to accomplish just that. So yeah.
You said for UWB, you said there's still some leftover frequency diversity in those small channels.
Okay, let me go back here. Okay. Now, I want you to, since I didn't draw the multipath channel, I want you to bear with me. And if I ask you, if this is my ultra wideband channel, okay, and if I wanted to find the equivalent multipath profile for this versus the equivalent multipath profile for this guy, equivalent multipath profile would be FFT of this frequency response. Equivalent for this one would be equivalent FFT response, FFT of this response. What are you going to find? That you're going to find that the support for this channel is much longer than this channel. It doesn't matter if there are less number of carriers. The interleaved nature of this makes it exploit full diversity. Because it's not narrowband, you actually can resolve much finer multipath than you can with a narrowband system. That is, in the ultra-wideband, for example, the one that we are talking about, the fact that you are interleaved like this, what does it physically mean? The only thing it physically means is you have 4 repetitions. It's the same as 8 to 16 in a way. It's basically, you have one transmission, very fast transmission, you just repeat that 4 times. And if you look at the standard body, that's the way they explain it. They say, okay, in the low rate, we just repeat the thing 4 times. They don't say why they repeat it 4 times. But the reason is because they have an interleaved arrangement to maximize its diversity. So when you repeat the same thing 4 times, you're still sampling at 500 mega samples per second. Okay? So your multipath resolution is 2 nanoseconds. Okay? So if you have a multipath support of, let's say, 50 nanoseconds, that corresponds to 25 samples. Okay? Regardless of the fact that you have these interleaved arrangements. So in an ultra-wideband system, you have 25 multipaths versus in a LAN environment, you have 1 multipath. So in a LAN environment, it makes sense that you try to maximize this diversity by putting multiple transmitter antennas, so you get some virtual multipaths effectively. So you convert that MIMO that you put in, effectively becomes some kind of, you can use it to optimize your diversity. But in the ultra-wideband, there is no need for that. You already have lots of multipaths that you can actually exploit for frequency diversity. So that's the basic idea. Now, the fact that you do not use those some of the subcarriers doesn't mean you do not have the diversity. I think you can think of it in the following way. The interleaved setups gives you a different way of sampling the frequency domain. Okay? The samples you get in the frequency domain, like the tips of those black arrows, are going to be farther apart. Maybe they will be less correlated, but still you'll be able to exploit the full diversity.
Yes, the catch is actually in the use of your beat. You may have very little correlation because it's so wideband. So what if you have 25 samples? Maybe most of them are below noise and you really can't measure.
That's an interesting observation. Actually, I would venture to say that maybe you don't have 25 multipath samples. Maybe you have 1 or 2 multipaths, but you can perhaps resolve them. Okay, and they are necessarily unresolvable in the ultra-wideband. So I would say that you probably could resolve 1 or 2 multipaths, whereas in the LAN case, maybe you cannot. Okay, so that's one appeal of the ultra-wideband. And then the diversity is really, if you think about the diversity in frequency domain especially, is not really how many multipaths you have. It's the support of your multipath. And that's why when I put the structure, I said, okay, you just feed back the support of the channel. You don't have to support everything, because the code design that you have only needs the maximum support. And you can just tune your coding structure to optimize how you exploit diversity. Yeah.
Could you just explain what is support? Is there not resolvable? What is support?
That's a very good question. Support is basically the maximum multipath that you expect, like the
resolvable.
Not I would call it resolvable. I would call it, if you say age of t, for example, right? Age of t equals something that's not equal to 0 greater than 0 for a certain interval, and after that you just say, okay, well, there is no multipath. When you convolve a channel with with some signal, you say that the channel has support for a certain range. You probably have some.
No, but it has to be the delay. The maximum delay. The draw the delay profile.
If you have delay profile, okay, so you assume that your channel is going to be whatever it is, and it's going to end up, and this is this maximum, for example, T max. Okay. After this point, your age of T is effectively very, very small, or it's equal to 0. So this we call support. Okay. So in a LAN environment, and in indoor environment, it's not really LAN issue. It's about 50 nanoseconds. Now, what this means in terms of the practical implementation is, the system designer's choice.
No, but wouldn't you think that 15 nanoseconds is really depending on the bandwidth you're measuring that 15 nanoseconds? In other words, for a very wideband system, very quickly you will lose correlation between, time delayed responses because it's such a wide band.
Well, I'm not so sure. I think these are really the physical propagation.
The channel impulse response actually will hardly change because of the bandwidth, because it actually depends on
the
how many
propagation
centers you have and how this thing. The correlation between different frequencies is certainly true, but what he is talking about is the just maximum. Your channel is FIR filter, so it just looks how many taps this is the last tap in the FIR filter. That's what's called support.
She's still measuring that H15 in a very way.
You're not really measuring that. You have some statistical assumption of what it is. Okay? And in most indoor systems, you can have those assumptions. You don't have to estimate that. You just say, well, you can estimate that and feed that back so you can design codes to be optimized to that support. But that doesn't have to be very exacting. And that's the neat thing about the diversity methods. They don't require you to exactly measure the channel, do some pre-coding, etc. They really are very, very loose. Now, but on the receiver, we just assume perfect channel, which that's something separate. Yeah.
Actually, the coherence bandwidth of your channel, because of the frequency and bandwidth, is actually larger than the frequency span of your one of your carriers. So the carriers are sort of not exactly flat.
Yes, that's true.
Because your carrier is like 5 meg. Well, it's a 5 to 20. Each of these 32 carriers are 5 megahertz broad, and the coherence frequency probably is 100 kilohertz or something.
This is an interesting point. This is indeed true. I make some approximations that indeed it is reasonably flat over them. Doesn't really matter.
It doesn't matter.
Yeah, doesn't really matter. So because you can put it in a discrete framework, and then you can operate on that. You can put a cyclic prefix type system, and then.
So you have a cyclic prefix covering your entire.
Support.
Yeah.
And I'll give another interesting tidbit. I was at Milcom 4 weeks ago or so. Actually, exactly 4 or 5 weeks ago. Okay. And there were some people from the military. They said, "Well, we don't care what the commercial world wants to do. We want to I want to design receivers that cost $10,000, but I want to use this ultra wideband system perhaps at 10 kilometers." So. What does that mean? Does that mean that maybe this thing is not useful? Why? Because it really depends on some kind of block structure, and it actually, if you think about the way it's constructed, as I said, it's 500 megahertz, it's 2 nanoseconds per sample. The block interval of this thing is 2 nanoseconds times 160, okay, 320 nanoseconds. Okay.
So 1 microsecond for each 300 meters.
That's right. That's right. That's right. That's right. So one of the things they were saying was, maybe we'll have our own systems. We'll not tie ourselves to these commercial systems. These commercial systems, I will let them do whatever they want. But the ultra wideband we understand will be perhaps different from this thing, which is for 315. Okay. So this is not the only ultra wideband that will be out there. Why? Because some people will try to spread their signals. They will say, we have a single sensor measurement, 1 second. We don't need to have all this bandwidth. And so there are actually intriguing things about how these systems do operate.
What kind of rate do they want? What kind of rate do they want? 1,000 kilometers.
Oh, they talk about extremely slow. For example, for ranging applications, they want to use ultra wideband, right? Like once every second. Right? Like maybe they do not need this. And this, if you think about, I'll tell you something else, of course. When we talk about exploiting this diversity, now ultra wideband is a very good way to exploit diversity, but you look at the block structure, it can't really handle the ultra wideband that's out there. It will not be able to handle the typical multipath beyond ARU, even NERU. Okay, so the real primary application of ultra wideband may be like streaming music from your PC to your stereo, replacing your monitor cable for whatever reason, and replacing your chip interconnects. It could very well be that that's what's going to happen because of the way that it is set up. But do you need MIMO for that? And my answer is probably not. So thank you for coming. And if you have any questions, yeah.
One more question about this. So for MIMO system, we have a model like a random matrix H,
right.
so that each item is ID Gaussian distribution. So here, when we have the frequency domain subchannels, what's the model? How to describe the is it statistical
I don't think
model for the frequency domain?
I don't think I mentioned that. Basically, you assume that the channel you generate in time domain,
yes.
okay? The time domain channel that you generate, you assume is a Rayleigh type fading, and then you generate from that you generate frequency domain realization, which becomes a correlated type of.
Okay, so basically you have model like you have multipath with independent Rayleigh.
Up to your support length, and then you create your channel based on that.
So how about the analysis? When you do analysis, there's space frequency coding. Do you also use the time domain model to analyze this? It seems very hard.
Not necessarily, because the thing you do is you generate random delays, okay, and you generate random delays based on the profile that you have, and then these random delays you have, depending on how many multipaths you generate. You're going to just say, okay, the main path is delta of t plus delta of t minus tau 1 plus delta of t minus tau 2, etc. And then you generate a Fourier transform of that, and that gives you a frequency selective channel.
Okay.
So it's not that.
You analyze those things based on the Fourier transform.
That's right. That's right. You do not assume all the channels are uncorrelated. You assume that they are correlated. You assume that they're coming from some likely type of physical channel. Also, people, when they started multi-carrier CDMA research, linear nets, etc., they generated a lot of hype because they assumed all these channels were independently fading, and so this was like superior CDMA, etc. No, we don't do that kind of tricks. We use the same channel models that established channel models that are used for all of this. All right, thank you again.